Leetcode series, question 1971. Given the number of nodes and edges of a graph, we need to find if path exists between the given source and destination vertices. Let's look at the first example. We have been given number of nodes equals to 3 and edges array which contains edges between 0 to 1, 1 to 2 and 2 to 0. And we are given source vertex as 0 and destination vertex as 2. And we have to find if path exists between 0 and 2. Hey there, I'm Shabhav and my goal is to help you clear your interviews by answering all the problem solving questions related to data structure and algorithms. The solution to this problem will be in JavaScript, but even if you are not a JavaScript developer, I would suggest you to at least go through the explanation of the solution to understand the concepts, and then I can guarantee you that you'll be able to code the solution in any language of your choice. So let's jump onto the problem. Let's first understand what a path means. A path between two vertices would exist if you start traversing from the source vertex and somehow manage to reach the destination. So for this question, if we can reach the destination vertex, we should return true, and if we can't reach the destination vertex, we should return false. So basically, we have to traverse the graph. It's a simple traversal problem, and we know there are two approaches of graph traversal, BFS and DFS. We can use either of these two. In this video, we will take a look into DFS approach, but BFS is also very similar, and once you understand one approach, you should be able to solve using the other approach on your own. Apart from these two approaches, this problem can also be solved using another approach known as union find method. Let me know in the comment section if you want me to prepare a video for that as well. So let's start with our DFS approach. For traversal, we are going to use the concept of adjacency list. Adjacency list is nothing but a collection of lists used to represent a graph. For each node, we would store all its adjacent vertices in an array. This will make the traversal very easy. I have already prepared a detailed video on this. If you are not familiar with adjacency list at all, I would advise you to pause this and go watch that video first. The link to that video is in description. Now, assuming you have a good understanding of adjacency list, let's understand how we do the traversal using DFS approach. We start with a node and traverse all the way down to the last reachable node. In our case, we would start from the source vertex 0, and remember, we have a given destination node, so while traversal at every step, we can check if this current node is same as the destination node. If yes, then that is our answer. So we will check if 0 is equal to destination. No. So we move forward. We will go to one of the zero's adjacent vertices, let's say 1. Then we compare 1 with the destination and it is also not the same. So again we move forward. Now since this is a depth first search, instead of looking for another adjacent vertex of 0, we would start looking for the adjacent vertices of 1 first. Adjacent vertices of 1 are 0 and 2. Now since we have already covered 0, it doesn't make sense to again go back to 0. If we go there, we will be stuck in the loop of 0 to 1 and 1 to 0. So for this, let's keep track of all the previously visited vertices in a set. Set because search operation in a set is order of 1 operation. So avoiding 0, we move on to the next vertex, which is 2. And like what we did earlier, after traversing to any node, we compare it to the destination vertex to check if they are same. In this case, 2 is indeed equal to the destination vertex. So here's our answer. We can return true. Now let's look at another example in which there's no path. This will help us cover our second use case as well. So now we have been given 6 vertices and the edges are between 0 to 1, 0 to 3, 1 to 2 and 4 to 5. Source is 0 and destination is 4. Following the same approach as the previous example, we will start with 0 and move to the first adjacent vertex 1. Then compare 1 with the destination vertex, and since they are not the same, we'll move forward to adjacent vertex of 1, which is 2. Again skipping 0 as it is already visited. Now 2 is also not the same as destination vertex, so we move forward to check the adjacent vertices of 2. But we find 2 has only one adjacent vertex, which is 1 and which is already visited. So we trace backward and try to find another adjacent vertex of 1. We see all the adjacent vertices of 1 are also visited. So we move back to 0. We have another adjacent vertex of 0, which is 3, and that is not previously visited. So we move to 3. 3 is not the destination, so we try to find a non-visited adjacent vertex of 3, but we can't find any, so go back to 0. Now all the adjacent vertices of 0 are visited, so we stop. And since we couldn't reach to our destination vertex 4, we return false from our function. Now let's try to write a working code for this. Let's start with the code for creating adjacency list. If you still don't have understanding about it, please watch my full video on adjacency list. Let's call this and store the adjacency list in a variable called graph, because essentially it's a graph only. Second, we would need our visited set. Now let's write our recursive function. We need recursion because in few cases we would need to backtrack to go to other neighbors of the node. We can also do it using stack instead of recursion, but here I am going with recursion. Stack would also be very similar. Let's call this recursive function with the given source and destination vertices. Now all our boilerplate code is done. Let's start with the actual logic. As we discussed, at every step we need to check if our source vertex is equal to destination vertex. If yes, then that is our answer, otherwise we will move forward. Now since we are visiting the source vertex, let's add it in the visited set and then move forward to check its neighbors. So we would write the for of loop to go through each of the neighbors. Now we have moved from the source to its neighbor, so this is our new source and the destination remains the same. But first, let's check if we have already visited this vertex before or not. If yes, we will skip it, otherwise we will call our function again with this new source and the destination to check if we can reach the destination from this new source. If yes, then that's our answer. If not, then we will backtrack and check for the next neighbor. If all the neighbors are exhausted and we have still not reached the destination, then we return false as we couldn't find a path to the destination from the source. And that's it. Our code is done. Let's run it and see if it's correct. Looks like it passed both the test cases. So let's submit and check if we are missing any edge cases. Okay, it got submitted successfully. All the test cases passed. So this is it, guys. To check if path exists in a graph, we just need to traverse through the graph from source to the destination vertex. If you have understood the concept, you can like, subscribe and end the video here. But if you are still confused regarding any step, let's do a code walkthrough with another example to understand the things thoroughly. We have this graph with 4 nodes. Source is 0 and destination is 3. First, we will create an adjacency list and initialize an empty set to keep track of visited vertices. Then, we will call our recursive function with the source as 0 and destination as 3. Now, let's understand this recursive function in detail. First, we will check if source 0 is same as destination 3 or not. No, so we move ahead. Now, since we are visiting 0, we add it inside the visited set. Then, we will go through all the neighbors of 0. We pick the first neighbor as 1 and check if 1 is already visited. No, it is first time we are seeing 1, so we move ahead and call our same recursive function now with a new source which is 1 and the same destination 3. This is because we know that we can reach to 1 from 0. Now if we can reach 3 from 1, then we can safely say that since I can go from 0 to 1 and 1 to 3, this means we can go from 0 to 3. So this is the reason we call this function recursively. But first let's find out if we can actually reach 3 from 1 or not. So let's check our function call of 1 to 3. Since this is a new function call, this will start afresh. So again check if source 1 is same as destination 3. No, so we go ahead and add it to the visited set. Then we will start picking up neighbors of 1, which is only 0. Now since we have already visited 0, we do not need to again call our recursive function with 0 to 3. We know it will end in an infinite loop of 0 to 1, 1 to and 1 to 0. So we skip it. Now since there is no other neighbor of 1, we return false from this function. This will take back our control to the caller function, which was check if path exists from 0 to 3. That means we are backtracking to 0 because we got to know that we cannot reach to 3 via 1. Now we will check for other neighbors of 0, which is 2. So call this function again from 2 to 3. We will do this quickly now. 2 is not the destination 3, so move ahead and add 2 to the visited set. Then check for all its neighbors, but 2 has only one neighbor 0, which is already visited. So we skip it and at the end return false that we cannot reach to 3 from 2. Now we again backtrack to 0. Now since there are no other neighbors of 0 and from the existing neighbors 1 and 2 we could not reach 3, this means there is no path from 0 to 3. So we return false at the end. I really hope you understood this concept thoroughly. If not, let me know in the comment section and I'll be happy to help you. Please like, subscribe and share with your friends. Thank you.